Okay, let's get started. So, as you saw, we finished the grading for the midterms, and the grades have all been posted on Courseworks. And we have the graded exams to hand back to you, but we have to give them to you in person just for privacy purposes. So the idea is you can go by the TA's office, Darwen's office tomorrow during his office hours, and pick them up then. So, and also, as you saw from his message, there was this, to me, surprising situation where we had a number of exams submitted where there was a correct answer but no intermediate working. And so we didn't give you any points for that. And I feel pretty uncomfortable about that because, what happened? You got the answer right. But it does say quite clearly that you have to show intermediate workings. And in particular, when the question involves sketching a curve or something, there is this obvious shortcut, which is just plug it into some system that will take a function and plot you the curve. And that completely misses the point, right? That's not, the test is not about whether you can correctly enter a function into a plotting program. And so that's why, it says you can't use a plotting function. And so unfortunately, because we can't tell what happened, and that there's the risk that that's what happened, we can't give any points for that. So, I'd much rather that I made it so that there was no way for you to do that, because, I don't want to give you no points. I want to make it so that you do the thing that allows you to get your points. But at this, when all that's all we have, we had no choice. So, and I can't. It's like clearly, if you'd known that was what was going to happen, you wouldn't have done that. So I'm sorry that somehow that was not adequately communicated. But hopefully now you understand the situation. For those of you who this concerns. If you want to talk to me about it, then you can come by my office. I'm probably not going to be around much this afternoon. I might be around between 2 and 3. Or if you want to set a time, then send me an email. We can set a time. Okay. Any questions? All right. So we are now we're dealing with this idea of how we can go about designing filters. We've got the basic tools. We know that it's possible to build systems that have this deliberate systematic effect on signals that go through them in terms of their frequency response, in terms of the magnitude of different frequency or Fourier components. And what we'd like to be able to do now is okay, fine. We know that they are out there. We sort of know that we can sort of hand build them by moving poles and zeros around to get the desired effect. But what's the systematic way that we can build filters with specific effects, specific parameters that we want? And so that's what we're going to learn about in the next couple of weeks. And there are these two broad classes of filters, FIR and IIR, finite impulse response, infinite impulse response. And they have sufficiently different characteristics that we have entirely different procedures for designing those two filters. So we're going to deal with them separately, and we're going to start off with the IIR filters. And the situation is such that the IIR filters, it's basically design of discrete time IIR filters is analogous to the design of continuous time IIR filters. Of course, continuous time filter design was the first thing to be developed because it was developed before we had computational methods for doing these processes, when we were just doing plain signal processing. And so rather than rederive them or reinvent it all for discrete time, the way we do it is we use the continuous time design procedures, and then we just have this mapping to convert our filter into discrete time. But it's slightly weird the way it happens, so we'll need to go through it. So what we're going to do in this slide pack is first we'll just talk about the general problem of how we design filters, what the specifications are going to be. Then we'll look at how we design filters in the analog domain, the particular kinds of filters that were developed for analog filters. And then we'll talk about how to actually map those filters into the discrete time domain to get our discrete time IIR filters. Okay, so the big picture of what we're doing when we're doing signal processing design is we start off with some problem we'd like to solve. We do some analysis on that problem, and typically what we're looking for is how can we convert this problem into a filter, or what part of this problem can we solve with a filter. And so if we're going to think about it in that respect, we're going to come up with some kind of magnitude response, maybe a phase response, and then some constraints on the cost or complexity. Typically we want to minimize the cost or complexity, but depending on where we are, there are different aspects that we want to minimize. So then we end up with these performance constraints in terms of the kinds of things that we can control in filter design. And then we actually do the design, which involves deciding whether we want an FIR or IR filter, what kind of filter within those classes, and then the order of the filter. And then once we've sort of made those choices, there's basically an equation or a function that just gives us the filter that satisfies those performance constraints. The output of this process is typically a filter designed in the abstract. That is the most neutral way of representing a discrete time system is through its transfer function. It's polynomial in Z. So that's kind of like an abstract description of the filter. And then we figured out how we're actually going to build it in terms of the structures that we were talking about last week, or whatever other infrastructure we're going to use to build it. So that's sort of separate from the design of the filter. And then the design of the filter then is, once you've got these performance constraints, that's relatively straightforward. Okay, so what are these performance constraints? We talked about this before when we were talking about the idea of an ideal filter. It's like, well, at the simplest level, we've got a pass band, we've got a stop band. We want to let the energy in the pass band through. We want to remove the energy in the stop band. But if we take a naive approach like that, we end up with these crazy filter designs with very, very long, indeed infinitely long impulse responses that we can't implement. And so we allow ourselves a little bit of slack. We relax the problem a little bit, which allows us to have well-behaved, sensibly, it gives us a more interesting design problem to work with as well. And so here, rather than having this sort of brick wall filter, here's a sketch of here's a plot of an actual typical filter response. We have a pass band, we have a stop band. But in the pass band, instead of requiring the gain to be 0 dB or 1 for all frequencies, we say, okay, there's going to be a little bit of ripple, or maybe there's going to be some ripple around here, that we have some range of values, which is typically close to 1, close to 0 dB, but there's a little bit of deviation that we'll tolerate. And then for all the frequencies in the pass band, we'll guarantee that the gain is going to be within this range, but we don't really mind where it's, exactly where it is. Similarly, in the stop band, we say, well, we'd like the gain to be negative infinity dB, like it to be 0, but if it goes a little bit higher, maybe we'll have some largest gain that we'll tolerate. So maybe, in this case, minus 28 dB, which is not that small, but there's some value here. It's like, as long as the gain is always below this minimum stop band attenuation, then okay, that's fine, we'll take that filter. And of course, these things we can make these larger if we're worried about this, but we're saying, okay, we're not insisting that it be infinity. It can be some finite value. And then, rather than saying that the edge of the pass band is the edge of the stop band, we'll recognize that there may be some region of frequencies in here where we need to do a transition between pass band and stop band, which is pretty obvious if you look at this, this curve here, which is the actual DTFT of an actual system. It's more or less a continuous function, right? I mean, it's got these asymptotes down here because we plot it against a log, but it's going to be some continuous function, so it can't go, from presumably there's a gap between our worst pass band gain and our largest stop band gain, so it has to have some frequencies in order to make that transition. And so we have separate pass band edge and stop band edge, and in between them we have a transition band, a range of frequencies where we don't constrain the gain at all. It says here that the optimal filter will touch here and here. That is, it'll be at the very lowest range of its pass band, just at the very highest frequency in the pass band. It'll be the largest value allowable in stop band at the lowest frequency in the stop band for this low pass filter. And that's because if it was actually not quite touching there, then it would mean there was a cheaper filter, a less well-performing filter that would touch there. And so it's sort of somehow the filter we're looking at is not the absolute optimal one. Or, alternatively, if it was here, then you could move the passband edge up a little bit and you get a narrower transition band, which would mean a better filter. So there's nothing necessarily magic about these points, but typically if you've specified it, then the specification will involve pushing out your limits so that those points touch there. We'll talk more about that later. So I guess that's it. There are three big parameters here: the amount of ripple here, the amount of head, the margin we have here, the worst case passband gain, and then the width of this transition band, how wide, how many frequencies we have to sacrifice to get our transition. So then, and here are those three parameters. We want the transition band to be as narrow as possible because the transition band is kind of like this, this stuff we have to give away. We have to relax on what's going to happen there. And typically, it might be part of if we've got stuff in the stop band that we really want to get rid of, then we might have to back off our stop band edge until we get rid of that. But then we're going to lose some of our pass band because it's going to be in the transition band now. So we want to make this as narrow as possible. We want to have as little ripple in the pass band as possible, because ripple in the pass band is essentially distorting the signal. Right? There's a little bit of extra, there's an unknown gain. For a particular frequency in the pass band, we don't know whether it's going to hit a maximum or a minimum of those ripples. There's some noise, if you like, that's being added to our energy there. And then at the same time, we want to attenuate the stop band as much as possible, so we want to make that as large as possible. Typically, within a given filter, we can improve any one of these, but then the other ones will pop up. Or we can try and improve both of them, and then the third one will pop up. And they're an interacting set of constraints. We can't push all of them down, or if we try and push all of them down, basically the cost of the filter is going to go up. So we can actually use a higher order filter, more memories, more multiplies, a higher order of the polynomial of z, and that will put us into a new design space where all these things are lower, and then we can start playing with them and trading off between them. But that's the sort of the shape of the problems that we deal with.
When
Yeah.
When you go to higher order filters,
Yeah.
don't you approach the problem of stability?
That's interesting. So we can improve. We can use higher order filters if we're prepared. If we've got the computational, if we're prepared to take the computational cost. If we have the layout space, or we have enough cycles in our processor to do it. But there is also there's a second order constraint, which is like, well, eventually, if you get up very, very high order filters, they do have stability problems, and so it's not unlimited how far you can go. And basically, there are things that are going to hit you. At some point, we're going to get to quantization noise effects and trying to get this attenuation down. And certainly, if you try to go over very, very narrow transition bands, then you're going to come up against stability issues, because suddenly you're going to have to do this with a lot of very, very carefully placed routes, which means that you're going to suffer from quantization errors in your parameters as well. So there are going to be computational issues that hit you at some point, but there's a regime before we get there where we're just okay, we're trying to go for a very low order filter, but it's not quite good enough, so we're going to go slightly higher. Yeah.
Sorry, I didn't understand. So when you close this, put those zeros really close,
Yeah.
is it a practical problem or is it a theoretical problem?
Right. Is it when you try and have very high order filters, meaning that you have to have very, very precise positioning of poles and zeros? It's not a theoretical problem. It's all the theoretical part is all math. Math works beautifully, regardless of how small the numbers are. It's a practical problem. And in particular, the analysis we're doing here is all about discrete time, the problems that come up when we sample in time. But with a real digital system, we also have quantization, which we almost never talk about in this class. But as you get to very, very sensitive systems, and the quantization of the actual coefficients, the fact that the numbers, the coefficients for your polynomial are being held as, whatever it is, 32-bit or 64-bit numbers, eventually that becomes significant and will hurt Okay, so let's look at these different parts of the sort of caricature of the frequency response separately. So let's look at the passband ripple. So we said the gain was going to be around 1 or around 0 dB. Now I've labeled it in linear units. And just we're going to allow it to deviate a little bit around there. By convention, and because it makes the math a little cleaner, we're going to say, okay, we're going to have the maximum gain be 1, and then allow it to dip down a little bit under 1, but rather than have it be around 1 in the middle here. So we allow them to make the maximum 1, and then we allow the minimum gain in the passband to be 1 over square root of 1 plus epsilon squared. So the idea is epsilon is a small number, epsilon squared is a small positive number, and then 1 plus epsilon squared is something, or 1 plus epsilon squared is a little bit more than 1. Square root of 1 plus epsilon squared is also just a little bit more than 1, so 1 over that is going to be slightly less than 1. Right? So we could have written that various ways, but again, by using it this way, it works out that some of the other equations end up looking simpler. But it's just a way of parameterizing a number which is a little bit less than 1 with some small parameter here. If we talk about it, we can also talk about it in the dB domain, in which case this would be 0, and this would be negative 20 log 10 of this, square root of 1 plus epsilon squared. And so we call that alpha max. It's without the minus sign, alpha max is how many dB down we allow ourselves to go. So it might be 1 or 2 dB, something like that, something small. The ripple depth. Okay, that's how just to introduce those parameters, those variable names. So the epsilon is like, that's something that will show up again and again. And then here now in the stop band, where we have our worst case stop band gain, we call that 1 over A, right? This gain in linear terms is going to be 1 over A, which is to say that since the gain in the passband was 1, if the worst case gain in the stop band is 1 over A, then the passband gain is A times larger than the stop band gain. So A is some large number like 10 or 100, which is how much smaller the energy in the stop band is going to be compared to the energy in the passband. In the worst case, it could be even more. It could be a larger ratio than that, but this is the worst case ratio. And we can also express this in dB by taking 20 log base 10 of A, which is now the number of dB down that the stop band is compared to the passband, or compared to the target gain in the passband. And we can call that alpha S. I guess alpha is typically going to show up here as some gain value in dB. All right, so that's basically how those are just the variables, how we're going to define these these magnitude responses. Now, we have to decide whether we're going to use FIR or IIR filters, because that's the sort of the top level of the design tree. And so here is, just to revise, the contrast between these. Okay, so FIR filters are the ones that only have zeros. They only have feed-forward components. They have no feedback. As a result, they're always stable, because instability only comes from poles. If there are no poles, then there's no opportunity for instability, right? Because you're just feeding stuff forward. So you put some energy in, eventually it'll fall out the bottom of your delay line, and so your output is going to go to 0 at some point. As we've seen, it's possible to design FIR filters that have linear phase. These symmetric impulse response filters will have linear phase, which is kind of cool, although, it's not. You can have lots of FIR filters that don't have linear phase, but it is at least available, which is something we don't know how to do in IIR. But there are drawbacks. Typically, we have to use high order. For a particular filter response, we're often looking at, orders of 10 or 100 taps to get the particular response that we want. Another drawback is that the filtering that we were previously familiar with before the advent of discrete time signal processing is basically disconnected from this. That these are a whole different space of filters, which is fine, but it just means if there was something clever that we thought up previously, then we're not going to be able to use it here. So in contrast to that, we have the IIR filters. IIR filters, infinite impulse response, do have feedback, meaning they do have poles and zeros. They have feedback, meaning that there's some delay coming from the output and feeding back to the interior of the calculation, which is what gives them the poles. And that means that, you know, if you have a structure like that, if you have a bad choice of parameters, you can end up having poles which are outside the unit circle, leading to an unstable filter. I mean, typically this wouldn't happen after you built your filter, but if you're in the process of designing a filter, then, you know, it's something that can, you know, it's a very bad thing when it happens, right? You come up with this calculation, you get some parameters, you plug it in, and basically, you know, in MATLAB you start getting nans or whatever, and it's just nasty. So it's, even though, you know, it's basically you did something wrong, if you get to there, it's nice to be in a space where it's like impossible to get for that to happen. Another disadvantage is that just because of the design procedures we're using, typically they're done in terms of the magnitude response, and the phase response is whatever it's going to be. And so the phase response is typically nonlinear, and so there are these kind of phase distortions that happen, and that's just the nature of the filter. When we're sort of inventing filtering, inventing signal processing in the mid-20th century, it's like it's enough of a problem to be able to directly control the magnitude. The fact that we sort of have to give up on phase. So these things typically don't have great phase characteristics, or you have to worry about the fact the phase is going to be distorted. On the plus side, we can get really high-performance filters with relatively low orders. That, you know, whereas an FIR filter with 1,000 points is not that unusual. An IIR filter with more than 20 poles is pretty rare, because if you do go to those larger filters, that's when you start getting hit with these stability problems. So on the one hand, you know, you have stability problems, but on the other hand, you typically don't even need to go into that regime, because you can get really high performance filters with really good stop band attenuation with relatively low orders. And how do we get them? We actually use the analog, the techniques and the mathematics that have been developed for analog filters. That's how we design our discrete time IIR filters, which is what we're going to learn about now. So hopefully that's sort of, you know, it's pretty simple. Let's just actually summarize. So the bottom line is, if you're worried about the computational expense, if you care about computational cost, then IIR filters are the obvious choice, because they, in terms of bang for the buck, they give you great results. You use just a few, multiplies and accumulates just a few poles and zeros, and you've got this filter with really, you know, clean characteristics. And plus, you know, we know how to build these really good ones because of all the effort that was put into developing analog signal processing. By contrast, if you don't care about computational cost at all, you might as well use a linear phase FIR filter, because you can design an FIR filter with a very similar magnitude response. It'll have a huge order, but you can do it, and you can make it linear phase to boot, so you actually control both the magnitude and the phase. So if the phase response is something that really matters, and phase response, remember, is the timing, the relative timing of different frequency components. So if you've got something where that matters, for instance, if you care about the shape of a waveform, because the shape results from the phase interactions of the different frequency components, then you're going to want to take advantage of the fact you can get these linear phase FIR filters, and FIR will be your design. But if the phase is unimportant, because, like, well, the timing of these things isn't so critical, you know, if it's approximately correct, we'll be okay, then you might as well go with an IIR filter, because then you don't get the phase, you don't get the phase control, but you get the same kind of effect with much less cost. Yeah.
But what if you really, really want to use an FIR filter because of cost and stuff? Can you not do phase correction with all-pass filter?
Okay, so if you care about phase, but you can't afford an FIR filter, you can't afford a 50th order filter, you can, or let's say you care about phase, but you're working in analog, so the FIR filters are not a possibility. Well, there's not nothing you can do, right? We've seen with all-pass filters that one of the motivations, perhaps the main motivation for those, was as a way of modifying the phase without changing the magnitude response. So yes, there are certainly things you can do which can try and fix up the phase, but actually it's a lot of work. I don't know, I mean, I've never really done it, and certainly it's not like you can just do it, control it arbitrarily. It's like, okay, here I'm going to try and control a phase at just a few frequencies, and you can see what you can do. Whereas with a linear phase filter, it's so nice, right? It's like, okay, there is no phase issue. There's maybe some delay. There's no relative phase, and so it's a lot more attractive. So yeah, these are not the only choices. You know, if it really matters, you can try and do something with the phase. But in general, it's going to be much easier to go with FIR.
Can you please list the applications of filter without linear phase?
So,
if it
yeah.
is not linear, then they are distortion.
Right. So why would you ever want to build a filter with phase distortion in it, right? Because it seems like you're just messing up your signal. But although phase distortion is messing up your signal, it's bad news. Typically, it's not terrible. It's not like you're. So if we think about it in terms of relative delay, you're building maybe an analog. You're building a low-pass filter, and there's a little bit of phase distortion. But the phase distortion may be orders of milliseconds. So maybe some frequency components will be skewed relative to others by thousandth of a second. If you're dealing with audio, that's not important to your listener. They're not going to notice a millisecond change, right? So then it's like, okay, there was some phase distortion, but we could have gone with a 10 times or 50 times higher order filter done in FIR. We would have gotten rid of the phase distortion, but in terms of the application, if it's like tone control on some stereo, that no one's going to notice, and so it's an engineering choice. It's like, what does it matter? So it's all about how precisely does your application rely on the phase of your components, and if it's like the IIR filter will distort them, but within some bounds, and you know what the bounds are. You can calculate what the phase distortion is going to be, and you can decide, is it acceptable for my application or not? Okay. So now we've seen the choices. I mean, it's kind of, as sort of technology advances and issues typically, the way it happens is computational cost becomes less and less of an issue. That, the processors become whatever it is, 10 times faster every 3 or 4 years. So why, the issues like, well, we had to use IIR filters in the past, but now we've got the computational power to use FIR filters, so why would we even do IIR? That's an interesting, that's a valid point. And it may be that, as time goes on, the need for IIR filters becomes less and less. But there are actually, maybe there's another advantage, which is that IIR filters just have because, this whole perspective we've taken of thinking about the performance of filters in terms of where the poles and zeros are and where they are relative to the unit circle. If you want to have an actual pass band there, if you want to have some frequencies that you keep, typically that means, well, I'm going to put poles near the unit circle for those frequencies I want to keep. And that's a very natural way to build a bandpass filter. You can do something similar in FIR, but you've only got zeros, so what you have to do then is put the zeros everywhere except where you want the frequency to go through. And then it becomes much less obvious how the actual behavior in the pass band depends on the exact positions of all these zeros. So when I'm just thinking about solving a problem very simply and sort of, intuitively, my instinct is always to go for an IIR filter with some poles and then sort of, put the poles where I want, figure out where the zeros, and maybe then go and use a design procedure to get the exact optimal values within that family. But it's a very natural thing to do. And so the FIR, it's a little less intuitive, and so it's a little less familiar to me. But, that's very much a matter of taste. But at the moment, anyway, we're still, certainly in the systems you will encounter, I expect that you'll see a lot of IIR filters. So right now, it's still an important and useful thing to know about. Okay, so we've done our analysis, we've looked at our costs and benefits, and we've decided that IIR is the way we want to go, now we have to learn about how to do the IIR filter design. So, as I said, the discrete time IIR filters are basically inherited from analog filters, continuous time filters. In the analog domain, as we remember, but as we haven't spoken about this semester, we have this transform domain, the Laplace transform, which is in terms of a variable s, which is sort of like the Z of the Z transform, but sort of not like it as well. But analog filter design is very much like the systems design we've seen so far in terms of the Z polynomial, but it's in terms of polynomial in S. It has poles and zeros and everything, or at least it certainly has poles. And the idea is that we're going to figure out how to get an H of Z from an H of S in such a way that if this H of S, this analog filter, has certain desirable properties, like gain at certain frequencies, we're going to preserve those properties in the H of Z, or at least map them in a way that makes it possible for us to design useful ones. As I said, the analog filter design process is very sophisticated. It feels to me like there were these amazing mathematicians at work on these problems in the mid-20th century, and they came up with these amazing solutions. It's like, how did you ever know that was going to work? But that's because they're mathematicians, and that's what they do. And so it's great to be able to draw on those results. So the end of the story is going to be we're going to figure out how to take an analog domain filter and map it to a discrete time domain to give us a filter that is close as possible the same. It can't be exactly the same because they deal with different spaces, but we'll see what that means. So before that, we have to learn how to design these analog filters, or we have to learn about the design of analog filters. So that's just, by way of justifying why we're now going to spend a lecture or so talking about analog filter design, even though this is a discrete time signal processing class. And so these analog filters means, the filters that they were building for radar systems in the 1950s and the filters they were building for TV systems in the 1960s and 70s. Transistors, discrete components, capacitors, inductors. And they got pretty good at it. They basically, this whole scenario of the idea of building a filter and having a magnitude response and having constraints on the magnitude response, that's where all that theory came from. It's like, okay, well, if that's what we want to do, if we want to have a filter that has the least ripple and the most stopband attenuation, then this is the math that's going to give us that, and these are the solutions that will work for us. And that's basically, we're going to look at 4 different kinds of filters, and they have 4 different families. And what differentiates them is whether they do have ripples or not. So we've got both the passband and the stopband, and we can actually say, no, ripples are just like too awful because now I don't know exactly what's going to happen. So rather than having ripples, I want the flattest possible filter response. And we can say we want flatness in the passband or the stopband or both or neither. And so that gives us 2 choices in 2 domains, gives us 4 different kinds of filter. And so we have families of filters that achieve all of these, that have all these properties. And in general, because it's nicer to be flat than to have ripples, by sacrificing the flatness and allowing ripples, we allow ourselves to improve the overall parameters. So typically, if we have the same maximum deviation in the passband stopband, we're going to get narrower and narrower transition bands. We're going to be able to get the stopband and passband closer together as we allow more ripples into our design. So we're going to go through these in order. Let's just first quickly refresh our minds and sort of switch gears into this continuous time, this Laplace domain of thinking. So here we've got the continuous time, the discrete time. So this is just to remind ourselves what this relates to. So in discrete time, we had our systems defined by the Z transform, which is here. It's here defined in terms of the impulse response of the system. This is the equivalent in analog. In the analog continuous time domain, we have the Laplace transform. So it's a function of S, this transform domain variable. And here it's very much looking the same. It's got an analog impulse response. It's the integral of the analog impulse response times e to the minus st, integrated over time. So it's because the impulse response is continuous, we have to use an integral instead of a sum. And then instead of being z to the minus n or s to the minus t, it's e to the s to the minus t, as it were. But otherwise, it's kind of the same. The nice thing about the Z transform is that when we evaluate it on the unit circle, when we set Z equal e to the j omega, we get the Fourier transform. And that's the nice thing about the Laplace transform as well. But instead of evaluating it on the unit circle, we evaluate it on the imaginary axis. So S is, again, a complex variable here. But here, the imaginary axis gives us the Fourier transform, as you can sort of see here, that we know that this is e to the minus j something t is looking like the Fourier transform, right? So that means we can think, again, in the same way that we thought about, we understood the z transform, the z polynomial, as a function over the z plane, right? It's a function that can be evaluated for all values of z, and then we had special interpretations of different parts of the z plane. The unit circle as the frequency response, and then wanting poles to be on the inside of the unit circle for a stable system. We have the same thing with the S plane. H of S is defined for all complex values of S. We can evaluate it on the imaginary axis to get the frequency response. And it turns out that if we want our systems to be stable, we want the real part of the poles to be negative. That is, we want the poles to be on the left-hand half plane. So it's very much the same kinds of things that we can see. It's just that the details of where they are different. We've got the frequency axis on a line and the poles as a half plane. One interesting consequence of that is, well, we saw, when we were looking at those transformations, those relationships between different z transforms, if I give you a polynomial in z, you can do a substitution for z. You get a new polynomial out, you just substitute in. And you can think about that as taking the surface and then either twisting or scaling the entire z-plane. Now, if we twist it, we end up with this nice thing with a circle that the frequency response values just get moved to different frequencies. If we scale it, it's not that good because we care about the unit circle. When we scale it, the unit circle ends up somewhere else. And so it's not that, if I have h of z, if I then do h of alpha z, it's something else. It's not necessarily that interesting. In the S-plane, rotation is a very strange thing to do. It doesn't help us at all. But scaling now is interesting because if I scale it, so if I have not h of s but h of alpha s, the left-hand half plane remains left-hand half plane. The imaginary axis remains the imaginary axis. But now all that's happened is that the frequency values on the imaginary axis have shifted to new frequencies. And so the nice thing about Laplace domain systems is if you just scale s, if you just substitute in a alpha s, then you still end up with a filter, a system whose frequency response you know. All that's happened is the frequency axis has been scaled by the factor alpha. And so that means that the idea of trying to change the breakpoint of a filter in the Laplace domain is trivial. You just scale all the, you basically have to take your factor and apply it to the coefficients depending on what order of s they corresponded to. You might have to raise it to some power, but it's just a very simple scaling operation to design a filter at a 10 times the frequency or something. So we'll see that sort of comes up in these analog filter design processes. What that means is basically when we try and design an analog filter, we design it to an idealized frequency, a frequency of 1, because then once we've got that thing, we can trivially scale it up to some other frequency that we care about. Okay, so getting back to these 4 different kinds of filters, let's start with the Butterworth filter. And the Butterworth filter is the first one. It's got flat response in both the pass band and stop band. And what that means is it looks like this. Of course, the response isn't actually flat, ideal, but it means it's got no ripples. So it's monotonic. This is a low-pass filter here. The gain is largest at omega equals 0, and it sort of looks kind of flat, which in this case means it has the largest number of derivatives. Of, the highest order derivatives are 0 at this point, but it means that it's slightly curving down. It's always getting slightly lower. It's monotonically decreasing as frequency increases, which begins to sort of take over here. Okay, now we can begin to see that the actual gain is not 1 anymore, and then this is the cutoff frequency keeps going down, and then it sort of flattens out here because this is on linear amplitude, so it's 0 is the asymptote here. But this is what the filter looks like. Nice low-pass response. The blue line here is for a 4th order Butterworth filter. If we go to higher order, so the dotted red line is a 10th order filter, it looks the same, but just the transition is sharper, right? That's what we said, that as we increase the order, we can make the transition band narrower, but everything else can stay the same. So the Butterworth filter, we can define it in terms of its magnitude response. This is typically the way that analog filter design works in terms of magnitude of h of j omega squared. And then this is actually the power response, right? It's the square of the magnitude response. And it's here. It's 1 over 1 plus omega divided by omega c to the 2n. So we have our omega variable. We normalize it by our cutoff frequency, omega c. And then we raise that to the power 2n. And then 1 over 1 plus that gives us our magnitude response. And so that does what we want. If omega is small relative to omega c, then this thing tends to 0, and the gain is approximately 1. As omega gets larger, this term, is not quite 0. So this whole thing becomes slightly larger than 1. The whole gain becomes slightly smaller than 1, which is this beginning to drop off. But this doesn't become significant until omega and omega c is getting close to 1, so that omega and omega c to 2n is now large, relatively large compared to 1. Once we get to omega c, at omega c, right, this thing is going to be 1 plus 1. So the magnitude squared is going to be a half, meaning the magnitude is 1 over root 2, or this is the half power point, the 3 dB point that we spoke about when we talked about filter cutoff frequencies. And so, by defining it in this way, we already have one of our kind of favorite reference points, the 3 dB cutoff frequency, as the parameter in this equation. Notice that on this frequency response, we're now dealing with capital omega, which is my convention for analog frequency, radians per second. And of course, analog frequency has no upper limit. You can keep going faster and faster. They look like frequency responses we've had before, where the normalized frequency, radians per sample, would go up to pi, and then at pi everything would stop because that's where we start getting aliasing. Here there's no upper limit, so when we draw these we just have to stop at some point, but it will carry on like this forever. Okay. Here's a different way of plotting those same, yeah. Yeah.
So in this case, the way we're defining the magnitude responses, assuming that omega c is basically the most dominant of all the other 2n minus 1, for the nth order filter. So assuming all the other n minus 1 poles are much lesser than omega c. Is that what we're assuming here, or?
I'm not quite sure what you're asking. I've defined this function here without really explaining why. But I'm saying, if I could build you a filter that had this response, let's see what its properties would be. Okay? And the properties are that, well, it's going to go down as omega increases. It's going to have this 3 dB point at omega c. And as n increases, it's going to get a sharper filter. So that's the definition of the filter. I haven't told you how to build one of these yet, or even if it is possible to build one. It'd be easy to write down a function and then say, oh, but we don't know how to do it. It turns out that we do. This is available and we know how to do it, which is why we're talking about it. But that'll sort of come at the end. Okay, how we actually do it. So that's what it is. And the n is something we choose. It's like whatever the order of the filter we're going to use. Yeah.
So we have two parameters, but actually it's just one parameter, right? Because as we increase n, like omega c can fluctuate with.
Well, that's interesting. So we have two parameters here, right? We have omega c and n. Here I've plotted two functions just varying n. I haven't plotted the variation in omega c. And in fact, I've plotted this as omega divided by omega c because it's sort of not interesting. If I changed omega c, the whole, it's this idea of scaling these S transform responses. I could scale the frequency axis so everything was stretched out, but it would look like the same curve. It would just be relabeling the axis, right? But it turns out that the frequency response only depends on omega divided by omega c. Now, for a different omega c, I'm going to have a different filter, but the shape will look the same once I normalize the frequency axis by that cutoff frequency. Here, the behavior is always just depends on this ratio of omega divided by omega c, and so that's a very simply behaved parameter. Does that make sense? Okay. And that's the, like I said, that's the flavor of these analog things that, once you design it for one frequency, you've basically got it for all frequencies. once it's only, the frequency axis is typically in terms of a ratio rather than absolute frequency. So this is the same plot, but now I'm plotting it as a log-log plot. So the magnitude axis is in dB, right? So it goes to 0 and then goes down to negative infinity. And the frequency axis, the analog frequency axis, is still omega and omega c, but it's just on a log scale. So here's omega equals omega c, 10 times 1/10. And this sort of, one of the things about a log axis is that you can't go down to 0 here because you just get closer and closer to 0, 10 to the minus 1, 10 to the minus 2. And we know that we can't get out to infinity anyway. This does go, so this axis sort of goes to infinity in both directions. But that's kind of the reality that they're of continuous time that does. You can get infinitely small, you can get infinitely long. They both exist. And so, but when we plot it on this log frequency axis, we have this nice property that now, if we just work it through, the log of this thing in terms of the log of this thing, this becomes a straight line. This monotonic decrease now becomes an asymptote of a slope of where the slope is proportional to n, and in terms of dB, it'll be a halving of power for every doubling in frequency for each order n, which means we have a slope here of minus 6.0206, or approximately minus 6 dB per octave. An octave is a doubling in frequency. That's just saying the slope here is proportional to n, or that as n gets larger, the slope becomes sharper. So, if you've worked in analog design, you're used to seeing that kind of thing. Yeah?
Where does that come from again?
Oh, so the log of 2, log base 10 of 2 is 0.30103. So 20 times the log base 10 of 2 is 6.0206, which we approximate as 6, and so that's the 6 dB per octave. Yeah?
So if we increase the order, so you increase the number of poles
Yeah.
in the system.
Yeah.
But wouldn't it only affect the slope if all the poles are on the same frequency? Because if I have a dominant pole, let's say 10 hertz, and then my other poles are like 200 hertz, like it's not gonna start decreasing before it gets to 200 hertz. So how does that work?
Yeah, that's interesting. So the idea here is that what I've said is the slope here depends on all the poles, right? The order n is the number of poles that we have. And so the question is, well, that sort of means they all have to be in play at the same time. Well, we haven't said where the poles are. And of course, the point about this Butterworth filter is that the poles are all carefully arranged to give us the exact behavior we want. But in general, that's going to be the case because, okay, I don't know if this is going to help or not, but the whole argument about the geometric behavior, the geometric way of figuring out what's going on in the z-plane, of course, works in the s-plane at all. That geometric argument was just about how to, understand the behavior of a system expressed as a polynomial on a complex plane. So if we have the s-plane now, right, so this is the real part of s and the imaginary part of s, and then I've got some h of s, and that h of s is going to have a bunch of poles somewhere. They're going to be in the left-hand half plane because we want them to be stable. And now I want to do the same thing of saying, well, what is the magnitude of h of j omega? Well, j omega is just the product of, so h of j omega is going to be, the product of these poles, so product of 1 minus, let's call it s minus lambda I, right? So this is something where it's a pole at lambda I, and then if I have a set of poles, it means that they're multiplied together, so I have a product of those things. But I'm interested in, this is h of s, and I'm interested in s equal j omega, which is this point somewhere on here. So here's s equal j omega, which is if I can figure out the value of h of s here, it's going to be the magnitude, it's going to be the gain of this system at this frequency. Well, I'm saying that it's the product of these vectors here, which are these lines from that point on the imaginary axis to each of the poles. And so it doesn't, and as my frequency goes up, typically when we're in this slope here, we're saying, okay, we're not close to any of the poles anymore. We're sort of going off into higher frequency. what happens here is all of these lines is getting longer, and it doesn't matter where the poles are exactly, they're all getting longer now. And so we get something where we've got 1 over this thing, which is approximately going to be just the frequency, right? That these lines, first order, are just going to be this distance here, which is just the frequency. And so we have 1 over the frequency to the nth power, which is this thing. For each pole, we have 1 over frequency. So it sort of makes sense, and I go through that just because I want to sort of reinforce the idea that thinking about it geometrically is a nice way to understand what's going on with these systems. Okay, so that's our log-log response. This is I mentioned the definition of flatness is actually that the nth derivative at 0 is 0. So, it just means that before you can even get some slope, you have to get the curvature to be non-zero, and then the derivative of curvature, the rate of change of curvature of the frequency has to be non-zero. So just if you can settle our derivatives to 0 at a point, then it's sort of the flatness extends out further. Okay, so that's the behavior of the Butterworth magnitude response. How do we actually use this to design a filter? So this is the point. We've sort of defined this filter in terms of this function. So like if you tell me omega c and n, I can plot the magnitude response. But typically, we want to do the other thing. We've got some particular values we want to achieve in the magnitude response, some frequencies where we want the gain to be large, some where we want it to be small, and we want to choose n and omega c to achieve that. And so basically, we've got this curve here where we know the shape of that curve. We've got these points we're trying to achieve. The Butterworth filter is defined in terms of the cutoff frequency, the 3 dB point, but maybe we don't care about the 3 dB point. We want some other gain point that we have to achieve, 1 over square root of 1 plus epsilon squared. And so we end up, in our classic specification, where we've got a maximum allowable pass band deviation, which is our ripple depth, but there's no ripple here, but maybe 1/2 ripple. And the maximum allowable pass band attenuation, we've got a couple of points here, so we're trying to find the particular Butterworth curve that meets those points. And so we can just plug them in. We can say, okay, well, here is the Butterworth function at omega p, right, whatever it is. We don't know n and omega c yet, but whatever it is, this is what the gain will be. And here's what we want the actual gain to be. We want it to be at least no smaller than 1 over 1 plus epsilon squared. This is the gain squared. So this is now the square of that limit here. Same here. Here's what the Butterworth thing is going to be at omega s, the stop band edge. And our constraint is we want that to be no larger than 1 over a, or the squared response to be 1 over a squared. So you can take these two things. They've got a couple of things we don't want in them. Let's say we're trying to figure out the order of the filter that we need in order to make this work. There's going to be a curve. As we raise the order, it's going to get sharper and sharper. So there's going to be some order where it'll fit. But what is that order? Well, it turns out we can combine these two equations to get an inequality for n. We basically have to get rid of the omega c by dividing these two. And so we cross multiply here. You get 1 plus epsilon squared is greater than 1 plus omega p on omega c to 2n. You subtract 1 from both sides, you get epsilon squared greater than omega c on omega p on omega c to 2n. Do the same thing here. You get a squared is less than 1 plus omega s on omega c to 2n. You then subtract this 1, so you get a squared minus 1 is less than omega s on omega c. Then you divide those two, and you get omega s on omega p to 2n is less than, the inequalities mean the division still works. You can still get it as an inequality. A squared minus 1 on epsilon squared. And then to get n out, you take the log of both sides, and you can divide through, and you get this expression for n. Right? So I didn't do that, but you can see that's going to work. So now by combining these two equations, we get an inequality of n. It says if n is at least half of the ratio of log base 10 of this, a squared minus 1 divided by epsilon squared. A squared is large for something with a very low stop band gain. Epsilon squared is small of something with a very small stop band ripple, so they're both going to make this thing larger, make n larger, divided by log base 10 of omega s and omega p. So the only thing that matters is the ratio of the stop band edge to the pass band edge. How many times the frequency of the stop band edge, of the pass band edge is the stop band edge. And then as this gets closer to 1, so the stop band edge gets closer and closer to the pass band edge, this thing gets close to 1, so the log of it gets close to 0. So we're dividing by something which is getting close to 0, so n is getting larger. So this has the right behavior. As we try and increase the stop band attenuation or decrease the pass band ripple or reduce the transition band, the ratio between the two frequencies of the transition band, n is going to get larger. But, that's just to check because it came from the math, so it must be right. So now we've got a design equation. If you tell me what these points are, I can tell you, yes, I can do that with a Butterworth filter, and here's what order it's going to have to be. And then you can decide whether you can afford that, whether that's going to be practical for you to build. These things, this a squared minus 1 and epsilon squared, shows up several times, so it has a name, or its reciprocal has a name, or its the square root of reciprocal has a name, K1, or the discrimination, which is something about how good the pass band ripple is compared to the stop band. And this thing, the ratio of the transition band edges, also has a variable, although again it's the reciprocal, and it's called the selectivity. I've never actually seen these names used, but that's from the tradition of analog filter design. That's what they were called. Okay, so now we know, yeah.
So, where is omega c located in this?
Omega 0.
Omega c.
Omega c, right. So omega c was divided out when we solved for this. Because it doesn't...
No, in the frequency response. In the response
Yes.
curve.
So here, this is linear frequency. This is magnitude h of a. So omega c is the 0.707 point, the 1 over root 2, which will be here. 3 dB, exactly, yeah. So the point is that, when we characterize these filters very broadly, we use the 3 dB point as a way of characterizing a filter family. But this is about the actual specification of my application. It was like, well, yeah, but 3 dB, I can't deal with 3 dB attenuation in my passband. My passband's got to be within half a dB. So then you back up the curve to that point. So now we're talking about this point, but there is, if it was 3 dB, then we'd be easy. It's like, okay, the actual passband edge I care about is 3 dB point, so I don't even have to, normalize that out. It's already there.
So omega p is where exactly my first transition starts.
Right. Omega p is, you're saying, well,
the highest, the most dominant pole.
No. It's not about the poles. It's just that you're trying to make this into a commodity. You're trying to say, I want to be able to design filters. I don't care how you do this, but I just want you to give me a filter that has within this range of frequencies has a gain that doesn't deviate from 1 by more than this amount. So this amount is 1 over square root of 1 plus epsilon squared, and omega p, 0 to omega p is the range of frequencies where we're going to tolerate that amount of deviation. But in the specification, we haven't said that it has to be monotonic. It's just saying, okay, because we're going to look at other filters that do other things in this range, but they're still going to have the same constraint that the gain has to stay between 1 and 1 over 1 plus square root of 1 plus epsilon squared up to that frequency range. Okay.
Is the region between omega p and omega is called as transition region?
Exactly. This is the transition band. Yeah, the transition region. Exactly. Thank you. Yeah.
So I have a question. So that you have the magnitude here, but the formula on the side is the power magnitude, and I'm confused.
Yeah. So this is the magnitude of h of a, the j omega, because that's typically what we've been plotting so far. When we looked at magnitude responses, we always plotted the magnitude. Now, when I specified this thing, the equation. Yeah, look at that. Okay. This is the magnitude, and the limit here is 1 over square root of 1 plus epsilon squared. But the actual point I'm pulling out here is in terms of the squared magnitude, which is what the Butterworth equation gives me, and the square of this value here, right? So this is not the actual value here. This is the square of this value here. But the point is this point on the curve gives me this relationship. Same here. The actual value here is 1 over a. But if I think about think about it in terms of squared magnitude, then this is the squared magnitude from the Butterworth filter, and this is the square of that value here. Right? So, and this is amplitude or intensity. This is power, which is just amplitude squared, which is how we talk about it. I think there is some kind of convention that maybe when they first start building signal processing systems, they're really concerned about power, because power is the thing that really matters. It's how much your resistor gets heated up when you feed this into a load. Whereas now we don't care so much about power because it's all notional anyway. It's all just numbers on the computer. So we're much happier working with amplitude. But clearly they're not profoundly different. Okay. All right, so we've defined the Butterworth filter in terms of its magnitude response, said that it has magnitude response. We've shown how having that definition will allow us to design a system that, using Butterworth, that meets some specifications. We haven't actually said what it is, so how do we actually get it? Traditionally, it's just something that you look up. You do this process, you figure out your order, you figure out your frequencies, you look it up in a handbook, and then you've got typically you've got some, historically, classically, you've got some circuit which has got some transistors or op-amps, and it just tells you you've got a few parameters, the resistors and the capacitors. You just read the values of those and you set them up. But of course, it does have an actual H of S, does have a polynomial, and so we can think about where its poles are. And so we can look at that, and it turns out this is what we get. That a Butterworth filter has this kind of pole zero diagram, has no zeros, has poles, has n poles for a nth order filter. And the poles are like this. They're on a semicircle in the left-hand half plane. They have to be in the left-hand half plane for stability. And they're uniformly spaced, but they're kind of offset, right? If they were the nth roots of 1, say, if this is 1, then they would lie on, the nth divisions of this unit circle. We saw that earlier in the z-plane. So instead, they're the odd-indexed 2nth roots of 1. No, sorry. They're the odd-indexed 4n roots of 1 on this circle. By keeping only the odd index, we end up with half of them, and then by keeping only the left-hand half plane, we end up with a quarter of them. So we take the circle, we divide it up into 4n parts, and then we keep every other one if the real part is negative. And that gives us n poles, which are these poles on this semicircle. And we can think about what these do to the magnitude response by thinking about this geometric procedure. There are a bunch of, for any value omega on the imaginary axis, there are a bunch of vectors here. We take length of those things, multiply them together, take 1 over that, and that gives us the magnitude response. It's clear that as we go up here, these vectors are all getting longer, and so the magnitude goes down. It's not totally clear what happens in the middle here, because we're moving around here. Some of these are getting longer, some of them are getting shorter. And of course, that's the point, that they're getting longer and shorter in just the right balance to keep this magnitude response flat and monotonic. Yeah?
Can you just repeat what is the number of poles somewhere that have the
Right. So the basic thing is we want the Butterworth. We're saying, okay, the interesting thing about Butterworth things is they fall on a semicircle like this. And we want them to be sort of symmetric, and it turns out they're uniformly spaced on this semicircle. So, for some, but there's n of them because it's an nth order system. So how am I going to get n equally spaced points on this circle that are symmetric around 0, because obviously positive and negative frequencies have got to be symmetric, and well, there are different ways we could do it, but this is the way it works out is that, well, we could have all these symmetric ones here. We don't want those poles on the frequency axis, obviously, because they would be unstable poles. So we need to have these uniformly spaced points. We're going to have to cross out the even-ordered ones because they're the ones that, well, this is a heuristic argument. This is how I remember what it is. It's like if you want to come up with a set of uniformly spaced poles on the unit circle, and I want to have n of them, then if I have if I have 4n of these divisions here, And then I cross out this half, and I've got 2n over here. And then if I want to avoid these ones, but keep it symmetric, then I should keep the odd-numbered ones. So then I just get n of them left. So I cross out every other one. I'm left with these n, and that's my half of my odd-indexed 4n roots of 4n division of the circle. You know, yeah, again, I'm presenting this more or less as a, it's just here's the answer. I don't know how you'd construct this. I don't know how you go about sort of saying, I want to find this polynomial that has this behavior and work it out. That's what I mean about the mathematicians, the input from the mathematicians here. But that's what they are, and it's sort of, the more you think about it, the more you see that it does work just because of the balance. And I was trying to come up with some argument about right-angled triangles, about why these things balance out, but I don't know. But I'm sure there is one there, and I'm sure it'd be fun to do. Okay, so let's just do a quick example of actually designing a Butterworth filter to some specifications. So here, we're going to see this a few times. In the blue box is the actual specification, the customer's requirements for this filter. And then we see what we do with that. So the requirement is we want a Butterworth filter. Okay, so they're telling us they want a maximally flat filter. We want 1 dB cutoff at 1 kilohertz and a minimum attenuation of 40 dB at 5 kilohertz. So this is basically telling us here's the passband edge, the minimum passband attenuation, the stop band edge, and the maximum passband attenuation, minimum stop band attenuation. Here it is plotted out that we're saying, okay, at 1 kilohertz, we're allowing ourselves to go down by 1 dB, and then we must have fallen to 40 dB down by 5 kilohertz. And so we can just plug these into our design equations, right? That we can, if this negative 1 dB is 1 over 1 plus epsilon squared, then we can work out that, we can convert that into we can convert negative 1 dB into a real number by just dividing it by 20 and raising 10 to that power. And basically, when we work that through, we can solve for epsilon, or epsilon squared. Similarly, if the stop band attenuation is 40 dB, that means 20 log base 10 of 1 over a is minus 40 dB, so a is 100, right? Because log base 10 of 100 is 2, so log base 10 of 1/100th is minus 2, and 20 times that is minus 40. And then the other thing we needed was the ratio of the stop band to pass band edge. So this is 5 kilohertz and 1 kilohertz, so the ratio is 5 here. And so we can just drop that into our equation, which was the log base 10 of a squared minus 1 over epsilon squared. The log of that ratio divided by the log base 10 of this ratio, and half of that. So that turns out this evaluates to 3.28. N has got to be larger than this, greater than or equal to. But of course, n has to be an integer. We can't have 3.28 poles. So the smallest integer we can have is 4. But if we have a fourth order system, then it's going to be able to meet these requirements. So now we've got n, and then it's a question of, well, what is omega c going to be? Because what is the 3 dB frequency for this particular filter? Well, again, typically the way we do this, we'd have a table of normalized magnitude responses, and it would say, well, for a fourth order Butterworth filter where the cutoff frequency, normalized cutoff frequency is 1, then the 1 dB point would be 0.845. It would be a lower frequency, right, because we're going further up the curve. So that means if we want 0.845 to correspond to 1 kilohertz, then we want omega c will be 1 over 1,000 divided by 0.845, which would be 1.184 kilohertz. So the 1 dB point would be 1,000 hertz. The 3 dB point would be 1.184 kilohertz for this fourth order Butterworth filter. And then we'd basically get a filter. We'd have our table which would tell us, well, if you wanted to build a 1 hertz filter, a fourth order Butterworth filter, then these would be the coefficient values. And then to get the 1.184 kilohertz filter, we just scale everything by 1,184. And that would give us our filter, because again, it's very simple to scale in frequency. Of course, MATLAB gives us a function which does all that automatically. It has the function butter. The return of butter is actually the filter polynomial here. And the arguments are the order, the cutoff frequency, and then the S here just says, oh, by the way, I want you to design me an analog filter, not a discrete time filter, because we'll see how to use that. It'll also convert it into a discrete time response eventually. But you can do that, and you get a magnitude response like this. So just to finish off, let's just do that in MATLAB, which I've done already. So actually, if you go to the MATLAB scripts, today's MATLAB script just goes through all this. Here is just solving for epsilon, so just solving this equation that epsilon squared is going to be that. That's just working the equation backwards to give us epsilon squared. And here's solving for A. And so then here's the actual design equation. So it's a half of log base 10 of A squared minus 1 on E squared divided by log base 10 of the ratio of those frequencies. And that gives us this 3.28. So we choose n equal 4. Here we can actually, we know the equation, so we can work out from the Butterworth equation if it's got a gain of 1 dB at some frequency, then what frequency is it going to have the gain of 3 dB at? That gives us our omega c, which is now in radians per second. And here it is in hertz. And so now we just drop this into Butter, and we get our B and A out. So, So B and A is there. So that the N is 4, and the omega c is this thing, which is what we thought it was, the 1.184 kilohertz. And so now we can just do frec S. So we had frec Z, which takes the polynomials for a Z function and plots the frequency response. Frec S does the same thing, but for the Laplace domain, because these are in the Laplace domain. And here is our magnitude and phase response for this filter, and this is now on a log-log scale. So here's it's in radians per second, so this is 1,000 radians per second. We actually want it in kilohertz. So what do I do here? I can just read it off. I can set up my own omega, my own W, my own set of frequencies, use frec S to calculate the magnitude response like this, and then plot them against the frequency response that I want. Okay, so that's a little nicer now. So now it's in hertz and in dB. And now if I zoom in here, you see the design requirement was to get a gain of 1 dB down at 1 kilohertz. And so here's 1,000 hertz, here's minus 1 dB, and we see we hit it directly, which of course is, that's what we expected. That was the requirement, just to show that it actually work. And then if we actually keep following this down, the other constraint was to try and get to minus 40 dB at 5 kilohertz. Turns out we're already at minus 40 dB by 3.8 kilohertz here, right? This is minus 40 dB. And then at 5 kilohertz, we're even further down, right? We're going to be at minus 50 dB, in fact. And that's just because if we'd been able to build a filter with 3.28 poles, then it would have been just at 40 dB down at 5 kilohertz. We built a filter that was better than that, right? We had 0.72 extra poles. Doesn't mean anything, but we had a filter that was more than we needed. And so because we designed the frequency response to just touch at minus 1 dB at the passband edge, then we got better than we expected at the stopband edge. That's just, it's going to be some other thing. We only had one parameter to change, but that is the result. Okay, any questions? All right, so we'll continue this on Wednesday.